So today we're going to talk about Earth's mantle and Earth's core. Earth's mantle is beneath the crust. It's made up of hot, solid, viscoelastic rock. Scientists know this because seismic waves, meteorites, and heat that comes from inside the planet. It's made up of mostly periodotite. Periodotite is mostly iron and magnesium. It's rare at the Earth's surface, and it's made mostly of olivine and pyroxene, so gemstones. Conduction occurs when energy is transferred by collisions between particles. The faster or hotter particles transfer energy to the slower, colder particles. That's because they're going to be moving faster, so they're going to be the ones hitting more often. They're the ones with more energy, so they're going to have to give it up. Convection is the transfer of energy through the motion of fluids. The heat source, in this case, the core, heats up the fluid. The warmer fluid, liquid, gas, is less dense, so it floats to the top. The cooler fluid sinks to the bottom where it gets heated. And I know we said that the mantle is a viscoelastic solid, but there's motion because of plate tectonics and all that, where the uh, subduction areas, so the parts where it's going underneath one plate to the other, it's getting pushed down, and so that's kind of forcing things around, and then it gets heated up, and it's got to go somewhere, so it goes back up, and that's where your um, uh, production zones are. I'm going to let you watch these videos on your own, as to not waste time on this video. Watching a video on a video seems kind of redundant. So I thought, there we go. The mantle is composed of solid peridotite. Conduction from the core heats the lower mantle. Mantle convection brings the hot material up toward the surface. It brings cooler material down towards the core. The core is mostly dense iron. Scientists know this because iron meteorites from the early solar system. Earth's density from calculations from Earth's rotation shows that there must be something as dense as metal in the core. If it was all as dense as the crust, then we wouldn't have the same rotational speeds. Seismic waves show that the outer core is liquid and the inner core is solid. Reason for that being is we've got those shadow zones where we don't have the seismic waves going through, because they can go through the solid, but they can't go through liquid or gas. And again, we know this inner core has to be solid because of the way that the waves travel, as well as the sheer density of the material. For there to be a magnetic field, there must be liquid metal that is convecting. If it were solid, the magnetic field wouldn't move or vary. So we know, we talked about this before, that the magnetic field shifts a little bit, might even flip from time to time, on average 200 to 300,000 years. And if it weren't mostly iron, cobalt, and nickel, it wouldn't have a permanent magnetic field, because these are the only three metals that of the transition metals that have permanent magnetic fields. The others can shift. There are a few rare earth magnetic materials, but again, rare earth, not lots of earth. Also, we know that it's got to be mostly iron because in normal solar production, iron is the highest atomic number that we can make. So, other than what happens in middle of solar collisions and supernova, we're not even going to get cobalt and nickel made. That makes them a lot rarer than, say, iron. And we can look at the other planets in our solar system and see how they behave, and do mathematical models to see that it's got to be mostly iron with maybe a little bit of something else. Again, there's a video that you can watch later. We don't need to watch it in this video. Density calculation shows that the Earth's core is metal. Seismic waves show that the inner core is solid and the outer core is liquid. Metallic meteorites and the magnetic field are also clues about the makeup of the core. So here is your homework. I know I didn't go over 320 notes. That's because it's, again, about the lithosphere and asthenosphere that we've already